All right, let's get into it. We're going to be looking at a pretty radical new take on a name you probably know, Johannes Keppler. Yeah, the planets guy. But what if the story we all got in science class left out the biggest part? We all learned about Kepler's laws of planetary motion, right? They're these super elegant rules that describe how the planets travel in their orbits. But the source material for this explainer says, hold on a second. It argues we've totally missed the most important piece of the puzzle, Kepler's own explanation for why they move in the first place. And this really gets to the heart of it. It's like there are two different Keplers. Was he just a brilliant celestial cartographer, mapping out the how? Or was he actually a physicist, proposing a real physical engine that drives the whole solar system? So yeah, this slide lays out the big debate perfectly. The mainstream view, right? Kepler described how planets move. His laws are just geometry, and he was basically the warm-up act for Newton and his theory of gravity. But the view we're exploring today is totally different. It says Kepler explained why they move, that his theory was about a physical mechanism, and that he wasn't just a prequel to Newton, he was maybe even a precursor to something like a unified field theory. Big stuff. So what was this grand theory, this forgotten mechanism? Well, according to this source, Kepler wasn't thinking about some mysterious, invisible force pulling things from a distance. Nope, he was thinking like an engineer. He imagined a tangible, physical engine right at the center of it all. Think less spooky action at a distance and more of a very real, very powerful push. And here's how that engine supposedly works, broken down step by step. First, the sun spins on its axis. As it spins, it's constantly emitting this physical field. Our source calls it a charge field, which you can think of as its light and energy. And this field, this radiation, physically pushes the planets, sweeping them along in their orbits. It's not a pull, it's a push, creating this massive swirling vortex in space. Now, this is absolutely crucial. The big problem with gravity, at least initially, is that you have to ask, why don't the planets just fall straight into the sun? Well, Newton's answer was that they already had some sideways motion, a tangential velocity that keeps them in orbit, but he never really explained where that sideways motion came from. This Kepler model, it solves that problem from the get-go. The sideways motion isn't a pre-existing condition, it's being generated constantly by the sun's spinning push. Okay, so this is a pretty wild idea, right? But the author of this theory isn't just making it up. They claim the evidence has been hiding in plain sight for 400 years, in Kepler's own notes and writings. So let's look at the clues. According to the source, Kepler laid out his reasoning pretty clearly. It was just simple observation and logic to him. 1. Planets farther from the sun move slower. Makes sense, right? The pushing force would be weaker out there. 2. Even in their own elliptical orbits, planets speed up when they get closer to the sun. Again, the force is stronger there. 3. What could this force be? Well, the sun is constantly pouring out light and heat, seems like the logical candidate. And 4, the final piece. The sun rotates, and it does so in the very same direction that the planets orbit. For Kepler, this was the smoking gun. And you don't have to take the author's word for it. They point to quotes like this, directly from Kepler himself. He talks about a virtue, a power from the sun's body, emitted in straight lines, like a very rapid vortex. I mean, come on. That doesn't sound like someone just describing geometry. That sounds like someone trying to describe a physical force field. But here's the part that is just mind-blowing. The source points out that Kepler's theory wasn't just an explanation after the fact, it was a prediction. Think about this. Before 1618, based only on how the planets moved, Kepler predicted that the sun itself must be spinning on its axis. He had no way of seeing it. Then, in 1618, Galileo points his telescope up, observes sunspots, and proves it. The sun spins. Kepler was right. It's an incredible piece of scientific deduction. Okay, so all of this builds up to the main event, the central mystery of this whole story. We're going to dive into Kepler's third law. It's a mathematical relationship that's been a pillar of physics for centuries. But what if we've completely misunderstood what it's actually telling us? So, Kepler's third law. It looks a little intimidating, but the idea is pretty simple. It says that the square of a planet's orbital period, that's the time it takes to make one full trip around the sun, which we call t, is proportional to the cube of its average distance from the sun, which we call r. But why? Why this specific kind of weird relationship? The period squared and the distance cubed. I mean, where does that 3/2 power come from? The source we're looking at makes a bold claim. The standard textbook derivation, the one we all learn, is basically a mathematical trick. It works on paper, but it totally obscures the real physics going on. So the way it's normally taught is you take Newton's formula for gravity, you set it equal to the formula for centripetal force, the force needed to keep something moving in a circle, and boom, you do a little algebra and out pops t squared is proportional to r cubed. But our author here says this is a huge mistake. It's a mathematical coincidence that just happens to work. By mashing these two forces together, we've blinded ourselves to what's really happening in the field. All right, so if the old way is wrong, what's the right way? Let's dig into the solution proposed by the source. It tosses out that old derivation and says, let's rethink the forces from the ground up, arguing that this is what Kepler was trying to tell us all along. And it all comes down to two separate effects working together. First step is the push force, the engine of the whole system. Remember that charged field of light and energy radiating from the sun? Well, as that energy spreads out into the vastness of three-dimensional space, it gets weaker. Its power dilutes. The source argues that this dilution follows an inverse cube law, so the strength of the push drops off with the cube of the distance, or r cubed. Okay, so what about gravity? In this model, gravity isn't the main driver of the orbit. It's more like a regulator. It's still pulling the planet inward, and it still follows that familiar inverse square law, dropping off with r squared. But here's the twist. The author thinks of its effect as reducing the planet's effective mass, or its inertia. So the farther out a planet is, the weaker the gravitational pull and the lighter it becomes, making it easier for that charge field to push around. And this is where it all comes together beautifully. The planet's orbital period, t, is basically the result of a cosmic tug-of-war. On one side, you have the sun's push, the charge field, which gets weaker by r cubed. This force wants to slow the planet down, making its orbital period longer. On the other side, you have gravity's pull, getting weaker by r squared. This makes the planet lighter and easier to push, which wants to speed it up and make the period shorter. The orbital period, then, is the ratio of these two competing forces, the push, proportional to r cubed, over the lightness effect from gravity, proportional to r squared. And what do you get when you combine them? T squared is proportional to r cubed. It just falls right out of the physics. Now, you might be asking, wait, why is it r cubed divided by r squared and not the other way around? And that's a great question. The answer, according to the source, is simple. What is the orbital period t measuring? It's measuring the time it takes to complete the sideways orbital motion. So the force that's causing that sideways motion, the push from the charge field, has to be the main driver. It has to be in the numerator of that ratio. It's the cause. The other is the effect. And that leads us to the final, really provocative thought that this source leaves us with. Could the key to a unified field theory, the holy grail of modern physics, have been hiding in Johannes Kepler's notebooks for 400 years? It's a wild thought, but it suggests that maybe, just maybe, by dismissing his physical ideas as just some old pre-Newtonian thinking, we miss something huge. What if we go back and read Kepler not as an astronomer, but as the brilliant physicist he might have been?